One extremely powerful feature of calculus is its ability to find maximum and minimum values of a function. These are called extreme values of a function. Now recall that when we had a single variable function y equals f of x defined on some domain D, there were several different classifications of extreme values. If your function has an absolute minimum at x equals a, then f of a is less than or equal to f of x for all points x in the domain of your function. So for example, this point right here would be the absolute minimum because its value is lower than every other value in the function's domain. If you have an absolute maximum at the point a, then the value of that function is higher than any other value of the function in your domain. And for example, in this case, this would be the absolute maximum. Now, you could have several absolute maxima or minima, depending on if they're all the same height. And remember that the absolute maximum or minimum of a function could be in the interior of the domain, like it is in this blue point, or it could be at the endpoint of a domain, like it is on this green point. Now, there's also another type of maximum and minimum point, and this is called a relative or a local minimum or maximum. Now, if your function has a relative minimum at a point x equals a, the value of your function is less than or equal to the value of its neighbors in some open interval that contains that point a, so somewhere nearby. Now, similarly, if you have a relative maximum, that means the value of your function is higher than the value of its neighboring points in some open interval containing that. So, for example, in this picture here, we would have some open interval centered at that point, and that point at the top of the bump is a relative maximum because its value is higher than the value of its neighboring points. All of these definitions, absolute and relative min and max, generalize directly over to functions of more than one variable. Now, we're going to focus on functions of two variables, but you could also define things for functions of many variables. So let's take our function f of x and y to be defined on some domain D in R2. We are going to define an absolute minimum as follows. So your function f is going to have an absolute minimum at a point AB if the value of the function at that point AB is less than or equal to the value of the function anywhere else in the domain. So you can see in the picture here at point A, we've got an absolute minimum because the height of that bump is lower or less than the height of the function anywhere else on that domain. At the same time, your function will have an absolute maximum if the value of the function at that point AB is greater than or equal to the value of the function at any other point in the domain D. Now remember that an absolute minimum or maximum can happen either in the interior of your domain, like it does for the minimum here, or it could happen at the boundary, at the endpoints of your domain, like it does for the absolute maximum. So a function will have a relative minimum if the value of the function at that point AB is less than or equal to the value of the function for all points in some open disk that contains that. So just in some local neighborhood. And you can see in the picture here at point C that we've got a relative minimum because the height of that valley is lower than any of its neighboring points. Now, similarly, your function will have a relative maximum at a point AB if the value of the function at that point is higher than the value of the function in every point in some open neighborhood containing that point. That occurs at the point B. Now, our goal with all of these definitions is to develop some procedure that's going to be able to locate and classify extrema. That is, we would like to be able to determine where any relative and absolute min and max are for our function, and we'd like to be able to distinguish whether they are relative or absolute. Now, the good news is most of these procedures have been developed for functions of a single variable, and so many of those ideas are used as the basis to generalize it to multivariable functions. Now, as before, we're going to focus our attention on a function of two variables, z of f at x and y, but you could generalize this to functions of more than two variables as well. Now remember that when we had a function of a single variable, there was something called Fermat's theorem. If you have the knowledge that you have a high point or low point, this theorem, which is proved in Calculus 1, tells you that if your function has an extremum, that is a minimum or a maximum, at your point x equals a, then the derivative is either 0 at that point or the derivative doesn't exist at that point. If you have a high point or low point, either you have a flat tangent line at that point, or you've got some sort of pokey thing, which means that the derivative doesn't exist there. Now note, there's a special definition here, something called a critical point. Now the critical point of a function, this is a point in your domain of the function f where f prime equals 0 or f prime doesn't exist. Essentially, we're trying to use Fermat's theorem in reverse. I'm going to start hunting for all of those places where I have zero derivatives and non-existent derivatives to see if they could potentially be an extremum. But of course, you learned in Calc 1, not all critical points are extreme points. And there are usually a couple of very simple examples to show this to you. So for example, if I have the function x cubed, its derivative is 3x squared, and it has only one critical point. Its critical point is at x equals 0, because at that point, f prime of 0 is 0. So what this is saying is if you take this cubic function, right there is where you have a flat tangent line, but this is neither a minimum or a maximum, because if you took some open interval around that point, it would not be the lowest point in that interval, or it would not be the highest point in that interval. Now we are going to generalize Fermat's theorem to a function of two variables. Now, even though we're going to discuss this only for a function of two variables, again, the ideas that we put forward here could allow it to generalize to a function of any number of finite variables. So suppose that my function f of x and y has a relative extremum at the point a and b. So the key here is to let g of x be a function where we keep the x value of the function free and then fix the y value at b. By Fermat's theorem, either g prime at a is equal to 0 or g prime at a doesn't exist. G prime of a in this particular case is the same as saying take the x partial derivative of this function of one variable. That tells us that either the x partial derivative at the point ab is 0 or the x partial derivative of the function at ab doesn't exist. Now similarly, if we let h of y be the value of this multivariable function where we fix a and let y be free, that means if we were to take the derivative of this function, it would be like taking the y partial derivative of a and y. By Fermat's theorem, that tells us that either h prime of b is 0 or h prime of b doesn't exist. Fy at AB is 0 or Fy at AB doesn't exist. And if you put all of this together, you can come up with the following result. If my function is differentiable, which is important here, and has a relative extremum at the point AB, then it turns out that the gradient of that function at the point AB, which is just the vector of these partial derivatives at the point AB, is either equal to the 0 vector or that the gradient vector does not exist at the point AB. So this is the extension of Fermat's theorem to a multivariable function. Now note, the directional derivative of your function at some point AB was simply defined as the gradient at that point dotted with the unit vector at that point. At a relative extremum, you know that the gradient has to be equal to the zero vector, and that implies then that the directional derivative of your function at that extreme point must also be zero. What this is telling you is if you have a relative maximum or minimum, you can choose any direction to move in. Either the derivative must be flat there, or it must not exist. So for example, you could have a cone where you've got some direction to move in. If you were to draw a plane here, the derivative doesn't exist. Now, similarly, we can define a critical point once again. So a critical point of a function of two variables is a point in its domain where the gradient of the function is either equal to the zero vector or the gradient does not exist. And this is a natural extension. Now, once again, this could apply to a function of many variables. So as an example, let's take our function f of x and y to be the paraboloid 1 minus x squared plus y squared. In this particular case, the gradient of the function is the vector of partial derivatives, so it's going to be negative 2x and negative 2y. This gradient vector will always exist, so the only critical point of this function is when the gradient is equal to the zero vector, or negative 2x, negative 2y is equal to the 0, 0, and that tells you that x has to be 0 and y has to be 0 to make this happen. So that means there's only one critical point of this function at the point 0, 0. Now, what we want to know is that whether this is a minimum or a maximum. Now, remember that if we were to take this critical point and plug it into the function, we would have the value of 1, whereas the value of the function for any other point x and y is always going to be less than or equal to 1. F of 0, 0 is always greater than or equal to f of x and y for all x and y points that live in R2. And that means that we have a relative and an absolute maximum at the point 0, 0. Now you can see this very straightforwardly. Remember that this is a paraboloid function that goes through the z-axis at 1. Right there, this is the only maximum point, the only extreme point that we have. As another example, let's take the function square root x squared plus y squared. If I were to find the gradient of this function, what I would have would be 1/2 1 over the square root of x squared plus y squared times the 2x, 1/2 1 over that same square root times a 2y. The 1/2 powers will cancel out, and I'll end up with this result. This gradient can't be 0 because the values that make it equal to the 0 vector also cause the denominator to be 0. There is only one critical point at x equals 0 and y equals 0. So 0, 0 is the critical point. Now this function has a value of 0 at its critical point. If you were to take any other value, square root of x squared plus y squared, by definition of that square root, it's going to be greater than or equal to 0. So what you're finding here is that f of 0, 0 is less than or equal to f of x and y for all x and y in R2. And that tells me that this point 0, 0 is both a relative and an absolute minimum for this function f. It's the only one. Now this function is a cone. It's the top half of a cone. And what we're seeing is that this point right here at the bottom, this is our absolute and our relative minimum. Now you have to be careful here. Not all critical points give extrema. And this is just like in the single variable case. If I were to take the function y squared minus x squared, its domain, once again, is all real numbers, just like the previous two examples. The gradient of this function is the vector negative 2x and 2y here. This gradient function exists for all x and y, so there's only one critical point, and that happens when the gradient is equal to 0. This occurs at the point 0, 0. F of 0 and 0 is equal to 0. But we can't make that type of argument that we made earlier, and a picture of this function will help to try to explain why that is. This function is a hyperbolic paraboloid. If we were to sit here at the point 0, 0, along x equals 0, my function here would be 0 and y squared. So along the line x equals 0, if I were to draw a plane here, if I were to move in the y direction here, all I would be doing would be increasing. However, if I were to go along y equals 0, the value of my function would be then negative x squared. Now, if I were to cut this with a different plane, what I would find is that the function would be decreasing. This point here is neither increasing in every direction nor decreasing. So we're going to define a new classification of point. A saddle point is a critical point that is neither a minimum or a maximum. It's called a saddle point precisely because of this type of function. It looks like a saddle. In some directions I increase, and in some directions I decrease.